What's up, calculus students? Let's do this lesson 3 homework on the product and the quotient rule. We learned that the derivative of products and the derivative of quotients not as easy as you may think. You can't just take the derivative of the first and the derivative of the second and multiply them together. Like this is the derivative of x cubed, this is the derivative of cos x.
I want one of those.
So that's wrong. Instead, if you have a product rule, I like to say you have like a first piece times a second, and then the derivative is going to be the derivative of the first, so I'll say first prime times the second plus the derivative of the second piece, maybe second prime goes there, the prime can go there. Derivative of the first times the second plus the derivative of the second times the first. Okay, so y prime, which we know is the same as dy dx because we are taking the derivative to get the tangent slope generating equation. So the tangent slopes of x cubed times cos x can be found by plugging in values into 3x squared, derivative first times the second, plus negative sine x times x cubed. Okay, this is fine. We don't have to simplify, especially if like we're just asked to plug in values. There are situations where we're trying to figure out when we have certain tangent slopes where it is beneficial to factor. Say if I ask you when we have like horizontal tangents or something like that, it's beneficial to have it factored. You need to be prepared to factor, but for these questions at the beginning, factoring is not necessary because we're just going to be asked to like plug in values into this. Plugging in values into this will give me slopes of this. This is x times sine x. The derivative will be derivative of the first times the second plus the derivative of the second times the first. I would not be able to factor this at all, okay? Now, what's very important, and I'm just going to throw in a new problem here. What if I have 5 sine x, okay? 5 sine x. 5 sine x, you might look at and be like, oh, that's a product. I need to use the product rule. But I'll show you it's not necessary. This is a constant times a function. If we have a constant times a function, we can use the constant multiple rule, which is like leave the constant, take the derivative of the function. If you did use the product rule, you would still get the right answer. You're just doing a lot of unnecessary work because the derivative of 5 is 0, right? It's a horizontal line. The slopes are always 0. So the derivative of the first is 0 times the second plus the derivative of the second times the first. Oh, that's the same as just the constant times the derivative of the function. So no product rule needed here. We talked about that in the lesson. If you have a quotient, I call it a top and a bottom. The derivative of a quotient is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Okay? It's just a rule that you'll have to know. There are ways for me to show you theoretically why this derivative is this, but it's actually not worth the time. If you just know what it is, you know what it is. So maybe you have that written down on the side somewhere. We have the derivative of the top times the bottom. Use parentheses if there's more than just one thing. That way you remember to like distribute things or like work inside the parentheses first. Minus the derivative of the bottom times the top all over the bottom squared. My cursor disappeared. There it is. Use parentheses when you're squaring the bottom. Now, if I were to square 2x minus 3, it's not 4x squared minus 9 or plus 9. you'd have to write it out twice and write it out as 2x minus 3 times 2x minus 3 and distribute everything. So make sure we don't make that mistake. But again, this is fine if we were to just plug in values. Like if I asked you, what's the slope of this at 1? I could plug in 1 everywhere and get a value. But if you're trying to like see when this gives us a specific number, it's going to be beneficial for you to simplify. Now, to simplify, the best thing to simplify is the numerator. The denominator distributing is not going to help us. But if we distribute the top, get 6x cubed minus 9x squared, and then here 2x cubed is 2x cubes. We realize we can like combine our x cubes, we can maybe factor the top, and this would help us potentially solve an equation where we have our tangent slope generator equal to a number. Will you be expected to do this? It's like, well, depending on the situation. If I ask you, hey, what's the slope of this at 1? Well, no need to simplify. You could just plug in 1. But if I ask you, when will this slope equal 0? Well, then you should probably set this factored form equal to 0. Realize 0 slopes occur when your numerator equals 0. So you get 0 and 9/4. And like, that's important to do. We need to be able to do that. We'll do some practice problems, some homework problems later in this homework where we're doing that. For right now, simplification not important. It's going to be nice for this one, so we might as well practice. Derivative of the top times the bottom minus the derivative of the bottom. The derivative of 1 minus x is -1 times the top all over the bottom squared. Another situation where you needed to simplify is like, say I give you a multiple choice problem, and I say, what's the derivative of this? You don't see this anywhere on your answers. So sometimes with multiple choice problems, they require you to simplify. And when you're required to simplify, like, you got to make sure you know how to simplify. And this is a nicely simplified one because the x's in the numerator will just go away. And we just have 1 over 1 minus x squared. Okay, so that's why we need to simplify, either for a multiple choice problem or we want to set derivatives equal to numbers. 2 more quotients, derivative of the top times the bottom. I use parentheses to denote multiplication. Know that you cannot multiply this x and this x, okay? Cosine x, this x is trapped by the cosine, so think of it as being inside the cosine. You can't like multiply this x and say this is cos x squared. Don't do that. I'm going to write not cos x squared minus the derivative of the bottom times the top all over the bottom squared. I cannot simplify this at all. I cannot cross off an x here. We would need an x in both locations. We don't have it. We have to factor out an x, make a product. If anything, we can just like rewrite it to make it look nicer. But there's no simplification that can be done here. Derivative of the top times the bottom minus the derivative of the bottom times the top. Don't multiply that x into that cos x all over the bottom squared. Know that sine x quantity being squared, that is the same as sine not x squared, but sine squared x. This is the notation for sine being squared. I wouldn't want to distribute this, right? Because this would take forever to distribute and then use the power rule for. So we'll just treat this as a first and a second. first function times the second function. So we take the derivative of the first, which is just 2x, times the second, use parentheses, plus the derivative of the second, use parentheses because it's longer than just one term. Derivative of 1 is 0. That's why the 1 disappears. Derivative of the second times the first. Okay? Now, could you distribute this and could you simplify? Yeah, you could if you really wanted to or had to. But notice, hey, find the slope of the tangents to the functions on the previous page at the following point. So if I asked you, hey guys, what is the slope at x equals pi over 2? Well, you don't need to factor to plug in pi over 2 here. You plug in pi over 2 into your unsimplified and you're fine. You have 3 pi over 2 squared, the cosine pi over 2 plus negative sine pi over 2 times pi over 2 cubed. Cosine of pi over 2 is 0, so this guy is just 0. Over here, the sine of pi over 2 is 1. And then pi over 2 cubed is pi cubed over 8. So the answer is negative pi cubed over 8. Okay? You would get the same thing if you plugged in pi over 2 here. You just have to distribute it and to like undo it. So like, again, simplified doesn't necessarily help you, especially when you're just plugging in. Let's find now f prime at 2. So I'm asking you, what is the derivative? What is the slope of the tangent? What is the instantaneous rate of change at, I guess I'm finding the y's at pi over 2. So both of these y's at pi over 2. What is the derivative? What is the slope of the tangent? What is the instantaneous rate of change of this y at pi over 2? There was nothing simplified, so I'm just going to plug it in here. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So the answer to this one is just 1. If I did the one that I just made up, I would see that the derivative is 0. Now let's go to f prime at 2. So I'm asking you, what is the slope of the tangent? What's the IROC of this function at x equals 2? You don't need to have the simplified version to plug 2 in. Like, let's see how you could just plug in 2 here, 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 and you'll be able to get a number. We don't have to have it simplified so it equals a number. So I get 4 squared, which is, make sure we multiply first. Don't multiply this 3 and that 2 first. 4 squared, which is, 2 squared, which is 4. Don't say it's 6 squared. 4 times 3, which is 12. Switch this to red. 4 minus 3 is 1. That's nice. 2 cubed is 8. Times 2 is 16. So I have 12 minus 16 in the top. And the bottom, I'm just going to have 1 squared, which is 1. So I find the slope of the tangent, which is the instantaneous rate of change of this function, how quickly this is changing, is negative 4. Remember the interpretation of this. At x equals 2, this function is going down 4 y's per x at that location. Okay, it's not on average, it's now right there. We're doing this f at 2. We're doing the g's at pi. So this f at 2, maybe like the simplified version is easy to find. Maybe we could easily plug in to the original or to the simplified. If I had it here, I'd have 1 times negative 1 plus 2. So negative 1 plus 2 is 1. And on the bottom, I'd have 1. So I'd have 1 over 1, which is 1. Or over here, if I do the simplified version, I see that 1 over 1 again. So I see that the instantaneous rate of change is 1. This function is increasing 1 y per x at x equals 2. I'm going to do the g's at pi. What is the slope of the tangent of this? Get the tangent slope generator, plug in pi. It's very easy if you have a tangent slope generator. Cosine of pi is -1. Sine of pi is 0. So I have negative pi over pi squared. I can cross off one of these pi's. We just have multiplication, so that's fine. And I get -1 over pi. How quickly is this changing at x equals pi? This function, sine x over x, is decreasing 1 over pi y's per x at that location. It's the instantaneous rate of change. Over here, plugging in pi, sine of pi is 0, cosine of pi is -1. Ooh, this is our first instance, maybe not our first instance, of a number over 0. Number over 0 is undefined. If we think about this as being a slope, and if we think about slopes being undefined, we see that this function has a vertical tangent because undefined slopes are vertical. That slope is undefined. What you'll be able to see if you graph x over sine x, you don't have to do this. Like, this is why calculus helps us understand graphs without having to graph. We actually realize that not only we don't have a vertical tangent, actually, like, whoop, go back into the original function. I can't plug in pi into the original function. The original function gives me pi over 0. That means I have a vertical tangent, not a vertical tangent, a vertical asymptote. So that was my bad, actually. I was wrong. I went too far and then just thought this meant that. This meant like vertical tangent. But in reality, if I checked, I could have realized, yo, you don't even have a point on the function at pi. You have a vertical asymptote at pi. Since you have a vertical asymptote at pi, you're not differentiable. You don't have a tangent slope. We talked about differentiability, how like if you don't have a point, you won't have a slope, whether it's at a hole, whether it's at a sharp point or vertical asymptote. If you don't have a point, you won't have a slope. And then I ask you to find h prime of 1. Yeah, it's not beneficial to simplify this to plug in 1. It just helps if I have it like this. I get 2. 6 minus 3 is 3. 12 minus 3 is 9. -1. 6 minus 9, I get -3. This function at x equals 1 has a tangent slope of -3. This function's instantaneous rate of change is -3 y's per x. It's decreasing at 3 y's per x at that location. Now we can do some fun stuff like find equations of tangent lines. We can visually see the work that we do. Remember, we just like point slope. And remember, slopes come from our tangent slope generators. That's what we get from f prime. The y values of f prime tells us the slopes of f. And this comes from a point on our function. If I plugged in 3 pi over 2 into my function, that gives me the y coordinate on the function. Boom, slope. So you got to do both. You got to plug in 3 pi over 2. Cosine of 3 pi over 2 is 0. So that's 0. I need to find the slope. How do you find the slope without a calculator? You find the tangent slope generator. Use the quotient rule. Oops. Working ahead a little bit. Guys, this is a tangent slope generator. I always see students make this mistake of they plug that in there. No. the y values of your tangent slope generator give you slopes. This is not a slope. This is a slope generator. Make sure you understand that the values the y values give you m's. Okay, the sine of 3 pi over 2 is -1. Make it that opposite. I got +1 times 3 pi over 2. The cosine of 3 pi over 2 is 0. I got 3 pi over 2 squared. One of these 3 pi over 2s will cancel with that 3 pi over 2 because that's like gone, giving us an answer of 1 over 3 pi over 2. I'm going to rewrite that so it's a little simpler. If you divide 3 pi over 2 into 1, you can just flip. It's like 1 times 2 over 3 pi. So I get 2 over 3 pi. Now let's see our handiwork because it's nice to do that. This is like the one time where like you can actually check. I mean, you could always do this if you wanted to, but we're set up to do it with the problem here where you can make sure you use parentheses or use alpha F1. Say y equals, I could add the 0 over or add the y1. Don't worry about distributing. It doesn't need to be y equals mx plus b. That'll work. And this will be my function, cos x over x. And at 3 pi over 2, I'm going to see the tangent. If I zoom in right at 3 pi over 2, should be able to see it better, our handiwork. Yeah, so our function actually ends up going up, and that's why this line, boom, is the tangent right there. Let's just make sure 3 pi over 2. Yeah, so right there, that fits perfectly. Okay, same thing here. Find the equation of the tangent line. So let's start with what we're trying to find. Again, slope will come from my tangent slope generator. Its y value. X is going to be 4. Y1 will be my y, the point on y, the point on the function at 4. So we got to do two things. We got to plug in 4. Square root of 4 is 2. 4 squared is 16. 16 minus 12 is 4. So I get a half. So that's going to go there. And now we got to find the tangent slope. So we need the tangent slope generator. Quotient, use the quotient rule. Square root, we write it as a half power. Power rule, bring down the power, subtract the power by 1. That's the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. It's not really advantageous to simplify this since we are just plugging in a number, so don't. I am just plugging in 4. I get 1/2 times 1 over root 4. We know that a negative 1/2 power is just like a positive 1/2 power in the denominator. Times 16 minus 12. I'll write that out. Minus 2 times 4, which is 8 root 4. Over 16 minus 12 squared. A little bit of legwork we got to do here, a little bit of arithmetic. I got a half times a half, which is a fourth. I got 4. I got 8 times 2, which is 16. And I got 4 squared, which is 16. That's 1 minus 16, so that's negative 15 over 16. So I think my equation, negative 15 over 16 times x minus 4 plus a half, again, like if you were to graph this, the quickest and easiest way to graph this would be to just add that y1 over. You get that equation. And like, let's see our handiwork here. You can always use alpha F1 if you're like freaked out about parentheses. You guys kind of stink at parentheses, so use that. There's my function. Here is my tangent equation. Let's zoom standard. Boom. Hits it right there. If I kept zoomed in, it would have looked nice, but I didn't. So let's zoom in over there anyways. There's my function. Like the square root of 12 is where we have a vertical asymptote. Boom. Gosh, it's nice. At 4. Beautiful. All right, now we get into some trickier ones where we're trying to figure out when this has specific tangent slopes. Don't forget, when you have a derivative, you can plug in to get slopes, but you can also take your derivative and see when we have certain slopes. We will be able to solve this equation to find locations of certain slopes. And the certain slopes are given here. So tangent to this, but parallel to this. Now, the only way I know what is the slope we're looking for is to figure out what is the slope of this line. Parallel lines like equal slopes. We remember that from our algebra classes. So I need to figure out what is the slope of this guy. I'm going to subtract the x, divide by 9, and I get, okay, negative 1/9. Okay, so I'm trying to figure out when this has a slope that equals negative 1/9, right? Doesn't that make sense? Like it's similar to the questions we've done before, but now their functions are a little bit more complicated. So we did take the derivative of this earlier. It might be good for you to practice this again if we didn't do it correctly the first time around. But x over 1 minus x, after simplifying, we got 1 over 1 minus x squared. Ooh, but this is different. This is x over x minus 1 squared. So we got to do it. We got to use the quotient rule, take the derivative of the top times the bottom, minus the derivative of the bottom times the top, over the bottom squared. I'm trying to figure out when does this tangent slope generator generate a tangent slope of negative 1/9. This is the situation where simplification is necessary. To solve this equation, it's going to be so much easier if we have a simplified derivative that enables us to do a little bit of algebra, a little bit of balancing. And we realize, oh, I just get negative 1 over x minus 1 squared, and that equals negative 1/9. Now we have to solve, okay? We have to be able to do this. We have to practice it. Like some of you like to cross multiply. I don't like to do that. I like to first say, okay, they're both negative on both sides. So get rid of the negative, multiply both sides by negative 1. Even. I like to flip both sides. You can flip both sides. It's just 1 over both sides. That's totally fine. Okay, that's the same as cross multiplying, but the 9 would be on the other side, and the x minus 1 squared would be on the other side. Now, from here, you have two options. You could square root both sides, but whenever we square root an unknown squared, this is where we get that plus or minus that shows up, and this is why you may think that the square root of 9 is plus or minus 3. It's not that the square root of 9 is plus or minus 3. It's that the unknown value could have been positive or negative. So we could square root both sides to start. and get x minus 1 equals plus or minus 3. And then solve two equations, like add 1 to positive 3 and you get 4. Add 1 to negative 3 and you get negative 2. Those are the two locations. But we're not done yet because we're asked to find the equation of the lines, not just the locations. The other way to do this is to distribute the x minus 1. Make sure you do it correctly. Write it as x minus 1 times x minus 1. Distribute everything. You get x squared minus 2x plus 1 equals 9. And now since we have a quadratic with x squareds and x's, move everything onto one side, set it equal to 0, factor to solve. So I have x squared minus 2x minus 8 equals 0. That's x minus 4x plus 2 equals 0. Again, we'll get negative 2 and 4. But I'm not done. I still want my equations. And then once we have the equations, we can graph them. We can see our beautiful handiwork. Okay? So y minus y1 equals m x minus x1. There's actually not much work to do here because you know two parts of these equations. You know an x coordinate. Minus the negative, same as plus positive. You know the slopes. You could double check this if you wanted to. If you plugged in to y prime negative 2 and 4, you know that the slopes are going to be negative 1/9. That's an easy way to check. Like, did I get it right? Plug in 4. 4 minus 1 is 3. 3 squared is 9. Negative 1 over 9. Plug in negative 2. Negative 2 minus 1. Negative 3 squared, 9. So we know the slopes have to be negative 1/9. All we actually need is the y coordinate. How do we get the y coordinate? We go back into the original equation. X over x plus 1. X minus 1. We plug in 4. 4 over 3. Is that y coordinate? We plug in negative 2. Negative 2 over negative 3. Which is positive 2/3. And boom, we have our equations. Let's see our handiwork just because it's fun. For me, at least. X over parentheses, or use alpha F1, x minus 1 is our equation. We got this line. I'm just going to graph this line just because I have it. I don't really care about the point, but there's that line. And now we have our two tangent lines that are going to be parallel to the first line, but they will be tangent to the function. Okay, ready? Here's my function. Oh, zoom standard. There's my function. Here's my first line. It's not tangent to anything. Here's one line that's tangent to my function, parallel to that line. Here's my other line that's tangent to the function, parallel to that line. Honestly, like, what would be nicer is if I move this line, doesn't matter where it's located, like down some more. That way I can see. There's my function. Here's the line that I need to be parallel to. It's not tangent, it's just a random line. There's one line that is parallel and tangent. There's another line that's parallel and tangent. So we have a set of 3 parallel lines, 2 of which are tangent to my function. Beautiful stuff. All right, now another one. Only we're parallel to 16x. So that means the slope's got to be 16. I got to figure out, when does this have a tangent slope that equals 16? So fortunately, I'm only asked to find the x-coordinate locations, not the lines. We could do the extra work so we can see, but let's just get the problem right here. So I got to find the tangent slope generator by taking the derivative. I got to take the quotient rule. I got to use the quotient rule to find the derivative. Take the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. If I were to just plug in x's, you could just plug in x's. But since I'm figuring out when this is equal to 16, it will help us if we simplify. So I have x plus 1 minus x over x plus 1 squared. The x's will cancel. I end up with this equation. 1 over x plus 1 squared equals 16. Oh, goodness, how am I going to solve this? Well, again, you can flip both sides, or like you can multiply then divide. I like to flip both sides. Just be careful. If you flip both sides, the right side gets flipped. It's going to be 1/16. Now, there are two ways to do this. You could distribute and then subtract and then factor, but it's going to be tougher than if you just square rooted both sides. Because I get that x plus 1, it is a plus or minus, but the square root of 1/16 I can do. The square root of 1 is 1. The square root of 16 is 4. So I get plus or minus 1/4. Now I just have to figure out, like, if I have negative 1/4 or positive 1/4 and I solve for x, I subtract 1. What do I get? Well, subtract 4/4 from 1/4, you get negative 3/4. Subtract 4/4 from negative 1/4, you get negative 5/4. So those two x locations, we will have tangent slopes that equal 16. Let's see, does that make sense? Like, will this function be increasing 16 y's per x at those two very close locations? Negative 3/4, we should be increasing quickly. Yeah, you see that slope? If you like thought of the tangent line, it'd be like, yeah, that looks like it's going to be steep. It's going to be like 16. And negative 5/4, it'd be the same thing, but on the other side, yeah, you could see that too. It's going to be like 16 makes sense. Okay, another question that asks you for equations. So end goal here, different from the last question, are a couple of these, one or a couple. Parallel to this, I need to solve for y, so I know what the slope is of this. Dividing by negative 2, negative 1 divided by negative 2, positive 1/2. 2 divided by negative 2, negative 1, that doesn't matter. We see that the slope of this is 1/2. Parallel lines equal slopes. We want tangent lines that have a slope of 1/2. So we will figure out when this happens. Let's find out. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. When does that equal 1/2? Since we're solving an equation, simplification really necessary. We get x plus 1. I'm going to turn this into a negative 1, so when I distribute, I don't make mistakes. This is a common thing with the quotient rule. People make mistakes with distributing the minus sign. This is a minus x, but this is a positive 1. That leaves me with no x's in the top, but a 2 over x plus 1 squared equal to 1/2. Now, again, what I like to do is flip both sides, get the x's up top. Now, what would I do to solve? It's like, well, dividing by 2, let's get rid of that. Multiply both sides by 2. And like, look how nice this equation ended up. Because I know, and again, two ways to do this, but like, might as well do the easier way, which I think is square rooting both sides and making sure you know that like this could be a positive or negative so that when you square, you get positive 4. So I get this plus or minus 2. Subtracting 1 from positive 2 is 1. Subtracting 1 from negative 2 gives us negative 3. So I get two locations, negative 3 and 1. Now I need my equations, which won't be too tough because I have two of the three pieces of information. I have the x coordinate. I have the slope. I just need the y coordinate. Plug in -3 into y to find the y coordinate. -3 minus 1 is -4. -3 plus 1 is -2, so I get +2. 1 minus 1 is 0. 1 plus 1 is 2, so that's 0. And let's see our handiwork, because I like to do it to make sure that I didn't make mistakes. Probably safer for you guys to alpha F1 if you were to graph. It's going to be parallel to this line, 1/2 x minus 1. My tangent lines, 1/2 x plus 3, add the 2 over, 1/2 x minus 1. Don't have to do anything because it's 0. And let's see it. There is my first line that is not, I'm going to move it over. Let's get that. Move it down a little bit more. That way we can see, like, that first line is not tangent. First line's not tangent. The next 2 lines will be tangent and parallel to that first line. Boom, that looks beautiful. Boom, that looks beautiful. Okay, cool stuff. Instantaneous rate of change of 12. Guys, that's the slope of a tangent. That's a derivative. They're all the same. 12. When will this have a tangent slope that equals 12? Let's find out. Quotient rule, derivative of the top times the bottom. Thank goodness it's just x coordinates. Minus the derivative of the bottom times the top. All over. Bottom squared. When does this equal 12? Beneficial for us to simplify. Distribute the negative, guys. Distribute the negative. -2x minus 1. You got to distribute the negative. The 2x's are gone. The -2 and the -1 are -3. Ooh, this is not going to work out nicely. Why do I say that? Did I make a mistake? This should probably be a +1. But then it wouldn't. Yeah. Why do I know this is going to be a problem? Because if I multiply by -3, I'll get a negative. We can't take a square root of a negative. So my bad. Error, 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 error. Change this to a +1. I bet you that works out well. Let's see. Derivative of the top times the bottom minus the derivative of the bottom times the top. How would that change the top? 2x plus 2 minus 2x minus 1. Yeah, I mean, this is fine. I'm going to be okay with this. It's not going to be nice, but it'll be correct. So, and that's an x plus 1. Why do I not love this? Is because I'm not going to get like whole number answers, but that's okay. It's good to see that sometimes like our answers aren't going to be pretty, but they're still our answers. We have this equation. I'm going to flip both sides. At least I can do it because I have a +1 left over. But when I square root, I can't square root 12 and get a whole number. That's okay. Like, it's okay to get plus or minus root 1/12. It's okay. It's what it is. But like, how do I write our answers? Guys, you got to be okay with this. I have a what do we have to do? We have to subtract 1 from both of these, right? I'm going to have a positive root 1/12 minus 1. That's an answer. Can you simplify it so it's one thing? No. No. You could maybe combine the 1 into that. No, like don't. Like, this is fine. And then you have a negative root 1/12 minus 1. That's an answer, and it's okay to get funky looking answers. A negative root 1/12 minus 1. Hopefully you saw that. The problem with the original problem was that we had like a -1, or it was a -2, which would have made this a -4. And if it was a -4, the solutions are imaginary, which means like there are no solutions. I won't do that to you. All right, horizontal tangent. Slopes are 0. When will this equation, when will it have a slope of 0? When will the tangent slope generator generate a slope of 0? Tangent slope generator of prime equals 0. Derivative of the top times the bottom. This is f prime. Minus the derivative of the bottom times the top. All over. Oh, it's ugly. All over the bottom squared. Set equal to 0. Now, great thing about 0 is that when you have a fraction that equals 0, as long as your bottom is not 0, because you're not allowed to have 0 over 0, if your top is 0, the whole thing's 0. So for this question, as long as I don't have a solution x equals 16, because x equals 16, there is no point there, like you'd have a number over 0. It's a horizontal, vertical asymptote. As long as an answer isn't 16, we're fine. I only have to pay attention to the numerator equal to 0. And that's easier to deal with, to worry about. I missed, my face is gone. 2x squared. I think I figured out how to bring my face back. That, and I got that. I'll bring it back in a second. So I distributed the 2x squared to the 2x to the x and the 2x to the -16. I have this, which simplifies to be x squared minus 32x, which is equal to 0. I'd factor. That's the easiest thing to do. And I get two easy solutions, one being 0, one being 32. Where's my face? Screen, Castify, webcam disappeared. Well, maybe it's gone forever. I know there was a fix. Whatever. All right. Well, sorry, guys. I'm gone. We only have a couple more questions to do. So here I am with my tablet. All right, horizontal tangent, same deal. When is our tangent slope generator going to generate a slope of 0? Take the derivative of the top times the bottom minus the derivative of the bottom times the top. When will that equal 0? Wait, all over the bottom squared. Why did I skip the bottom? Because I know I can. Because I know I don't have to worry about it. So it's really just the top because you have 0 as long as the bottom is a number, which it will be because the bottom will never equal 0. X squared will always be positive, plus 16 positive. So I distribute, I get 2x squared plus 32 minus 4x squared. I'm a little bit concerned. I might not like this problem. Why am I a little bit concerned? Oh no, I think I'm going to be fine. I think I'm going to be just fine. Because I have negative 2x squared plus 32 equals 0. Oh, subtract 32. Divide by negative 2. Square root. Boom. X coordinate locations, we could see that if we wanted to. Alpha F1 fraction 2x over x squared plus 16. At negative 4 and at positive 4. You can't probably see it, but this function kind of goes down and goes up. So let's just zoom in on one location, negative 4. And you can see like it's going down, but it's going up. Maybe you don't see it, but like at negative 4, it's completely flat. It goes down, flattens out, goes up. All right, same deal. Hopefully we're getting bored of these, but it's good practice. Don't care about the bottom as long as one of the answers is not 2. We get 4x squared minus 8x minus 2x squared equals 0. 2x squared minus 8x equals 0. This one I got to factor. I'm going to factor out a 2x. And I get x equals 0 and 4. I think the last two are a little bit funky. Good practice, though. I think we'll have to do a little bit of simplification and factoring to the top times the bottom being longer, minus the derivative of the bottom, which is a product, times the top, which is like multiple things. Use parentheses, guys. Over the bottom squared. Guys, I'm going to skip the whole bottom squared because I know I need to set this equal to 0. So I don't really care about the bottom, okay? Because as long as the bottom doesn't equal 0, I'm going to be fine. Now, I got x squared plus x plus 4. These parentheses are gone. I just distributed one. I'm going to, there's two things you could do. You could distribute this negative into one of these, or you just say, yo, minus whatever we have here, okay? And what we have here, we can find by distributing. So I'm going to leave that minus sign there. I'm going to distribute it in later. So I have 2x squared plus 2x, 2x squared plus 2x plus 1x plus 1. And now I see I have a negative, a negative, a negative, a negative. Well, hold on, guys. Slow down, slow down. 2x plus 1x is 3x. 2x is 3x. All right, a negative, a negative, a negative. That helps me when I simplify because I have a negative x squared. X minus 3x is a minus 2x, and a 4 minus 1 is a positive 3. Now, you can divide negative 1 out of all of these terms. All of these terms you could divide by negative 1, but I'm going to caution you from doing that for the future. In the future, signs of our derivatives are super important. So what I'm going to tell you to do is to actually just factor out the negative. That way you know it's still there. And this is important for the future, okay? Important for the future is making sure that like things don't disappear on you, or else it'll hurt you in the long run. We can factor x squared plus 2x minus 3. That's x plus 3x minus 1. So the negative 1 does nothing. It doesn't mean 0 is a solution. The solutions are negative 3 and 1. Okay? Good. I believe this one is very similar to that. Lots of distribution and ugliness, but let's go. Horizontal tangents again. Our derivative of the top. Wrong. Times the bottom. That's gross. Oh, why did I give you this problem? Minus the derivative of the bottom times the top all over the bottom square. Yo, if you're still paying attention to this video, I'm not giving you something this complex on your quiz. For your quiz, expect to have stuff more like this, that, and then parallels these. Okay? So like the last one, definitely you don't have to worry about. Because look at this. Oh, this is going to be gross. We got to distribute all this grossness. All right, so let's do it. Because it's there. 2x cubed plus 6x squared plus negative 2x. I've just distributed the 2x. Plus 2x squared plus 6x minus 2. I just distributed the 2. Minus, big old set of parentheses for what we're going to get. I needed more space. 2x cubed plus 4x squared plus 2x plus 3x squared plus 6x plus 3. Two x cubed plus 8x squared plus 4x minus 2 minus 2x cubed, x cubes are going to be gone, plus 7x squared plus 8x plus 3. Some of that stuff's going to be gone. Distribute the negative. Two x cubes, they gone. 8x squareds and negative 7x squareds, 1x squared. 4x's, negative 8x's, negative 4x's, they gone. Minus 2, minus 3. Set that equal to 0. Yeah, you heard that. Factors solve. Bingo, bango, boongo. Yo, look at me. This is Mr. Mester being like, yo, good job. You did it. This is tough homework. Lots of stuff. Yo, if you're trying to do this without showing a lot of work, if you're not neat and orderly, paying attention to all the details, you're going to struggle. This is me being like, yo, you're going to struggle. Yo, you're going to struggle. Come on, man. And then, yeah, hopefully this practice is helpful for our quiz. Later.